Okay, welcome back. Let us consider the conformations of systems where there are atoms, like where there is no possibility of steric strain or maybe much less steric strain. Every atom has a size, even hydrogen there is some strain is there, as I said 10% of it contributes to the overall energy. However, the steric strain is less where there is no possibility of hydrogen bond, but where there is possibility of dipole-dipole repulsion. Okay. So, in that case what happens to the gauche form and to the antiform? So, obviously, at that point the gauche form will be less stable than the antiform. So, this was the hydrogen bond scenario we discussed last time, that if you have OH and X in the next atom, next carbon atom, then there is a possibility of hydrogen bond which stabilizes the system. If you have in this case, now we have the same system, but we have put the methyl groups here also. Earlier it was only ethylene glycol. If you put two methyl groups, now you know that this molecule can exist in either in a mesoform or it can exist in as a DL pair, a mesoform or a DL pair. If you consider the mesoform, what you are seeing is that this is the form where there is a hydrogen bond formation. Okay. Although while doing so you are bringing the two methyls in the gauche form. Okay. So, I can draw it in the board. So, what we are saying, I think this was the molecule OH, a methyl, hydrogen. So, when we draw the Newman projection of this, I think I told you that it is better to look from down. So, suppose this is 1, this is 2, this is 3, this is 4. So, what happens? This is the down methyl, that means the number 1, this is the number 2. So, number 2, the hydrogen goes on the right direction and the OH goes to the left, and this is the hydrogen and this is the OH and this is the other methyl. So, that is the direct conversion to the Newman projection. However, this is the eclipsed, fully eclipsed form. So, it will not exist in this form. So, it will try to exist if we follow the N-butane type of system, that scenario where the methyls are opposite to each other, anti to each other. So, what you do, you keep the front, suppose we keep the front carbon same and we rotate the back carbon by 180. So, if we do that, this methyl will be anti and this is OH and this OH will be here and this is the hydrogen. So, this should have been the most stable one, but the problem is there is no possibility of hydrogen bond formation here. So, if you convert it into the gauche form, where, so how to convert it into the gauche form? So, you take the OH here, suppose you bring the OH here, sorry, one OH was already there. So, now you have the hydrogen bond here, you have the top carbon remaining the same. So, do not change the top carbon, the back carbon, the OH is rotated and by 120 degree. So, the rotation was by 120. So, OH comes here, hydrogen goes there and the methyl comes here. It is the same what was actually written there, it is in different using a different type of Newman projection, okay. But they are same. If you see there is methyl-methyl interaction, Gauche-butane interaction, but there is hydrogen bond formation. So, the question is which one is more stable? Here the methyl-methyl is anti, there is no Gauche-butane interaction, but the OH cannot form hydrogen bond. Here the methyl-methyl has Gauche-butane interaction, but the OH can have hydrogen bond scenario. Okay. So, this is a very interesting case. So, which one predominates? Actually, hydrogen bond predominates over the methyl-methyl Gauss-Butane interactions. So, if you study the conformation, if you can detect the presence of these two, you will see that this will be the major form and this will be the minor form, because hydrogen bond, intramolecular hydrogen bond is the more stabilizing factor over the Gauss-Butane interaction. Okay. So, that is why I brought this case here. In case of 1,2-dibromoethane, so what will happen in case of 1,2-dibromoethane? I think it is written in a Fischer projection formula, but actually it does not require, because it is an achiral molecule, completely achiral molecule, and these two completely achiral molecules, this is CH2Br and CH2Br. But if you write it in a Fischer projection, it may look like this, that I put the Br on the right side and this Br on the left side. But again, keep in mind, this does not make any, there will be no difference if I put the Br here and the hydrogen here. It is the same molecule, because it is a achiral molecule. You can draw it in whatever way you like it. So, I just draw it in this type of Fischer projection. Okay. So, if this is the Fischer projection of the molecule 1,2-dibromoethane, so from this I said that always you look from the bottom side. If you do that, then this hydrogen will be this hydrogen, and on the right is this hydrogen, and on the left this bromine. This is the top carbon. So, I am looking from this bottom side, looking at this carbon, and this carbon now becomes the top carbon, because this is closer to me, and this carbon becomes the back carbon. And the back carbon, what happens? The bromine is to the right, this hydrogen is to the left, and this hydrogen will eclipse this hydrogen. So, that hydrogen is here. So, this is the conformation, okay, one of the conformations. Now, you try to you rotate it. This is the one which is the antiform. This is the one which is the eclipsed form, but this is partially eclipsed. You can have a fully eclipsed form also, where the bromine and bromine will fully eclipse each other. Okay. So, which will be the most stable one? I can actually I can do it here. I think all the conformations are not drawn in that picture. So, better draw all the conformations here. So, what we have started with? We have started with a bromine, so here, and a bromine there, hydrogen, hydrogen, hydrogen and hydrogen. So, now we convert it into the Newman projection. We are actually seeing it from this side. Okay. If we do that, then this will be a hydrogen, that will be a hydrogen, this will be the bromine, and on the right side there will be the back side of the carbon, the back carbon, the right hand side will be bromine, and this will be hydrogen, and that will be another hydrogen. So, this is the direct Newman projection formula of this conversion of this to the Newman projection. Now, you start rotating it. Okay. So, you can have, if you start, suppose I rotate the back carbon by 60 degree, say anti-clockwise, that means this. So, I rotate it by 60. So, if I do that, remember the back carbon. So, the front carbon do not gets disturbed. So, this is the front carbon, hydrogen and hydrogen, and this is the back carbon. So, this is the bromine, that is hydrogen, this is hydrogen. Now, like your earlier N-butane, so this is the Gauss form, the bromine and bromine has a dihedral angle of 60 degree. So, then you further rotate it and further rotate it by 60 degrees. So, what will happen? So, the bromine and the bromines will be eclipsing each other. So, that is the fully eclipsed form. Then you further rotate, and what you will get is another gauche form, the bromine having a diagonal angle of 60, hydrogen. Okay. So, the likewise you rotate. So, this is you started from here 60, then 60. This is what you remember, you started from a partially eclipsed one, okay, partially eclipsed, then a gauche form. So, this is partially eclipsed, this is a gauche form, this is fully eclipsed, F eclipsed, fully eclipsed, this is another gauche form, and then you rotate it and you get the bromine here, hydrogen, and you have another partially eclipsed form. This bromine hydrogen will be eclipsing each other, and there will be an eclipsing interaction here, hydrogen bromine. So, that is another 60 degree. So, 60 degree, this is 60 degree, and then you have the, because I want to come to the anti form. So, ultimately you will come to the remember the top one, do not disturb that, the top one remains the same. So, now you come to a position which is the anti form. Okay. So, this is the anti form and this is the partially eclipsed form. So, likewise you can continue. Okay. So, out of this which one is the most stable? Here the gauche form will not be that stable. First of all, bromine is quite, it is quite big, it is not a very small atom, it is quite big, but the important point is that it has got, it is because the CBr, the carbon is more electropositive, bromine is more electronegative. So, there will be polarization. So, that creates a dipole. So, there will be a dipole repulsion now, and that repulsion will make it less stable than the anti form, where it is the least, because they are anti to each other, and they are anti to each other. Okay. So, in this case, when you have this halogen at the 1 and 2 position, you see the anti form becomes more stable and not the gauche form. The reason here is there is dipole repulsion in the gauche form, that is why, which makes it less stable. Okay. Now, in case of you put a methyl now, what will be the situation? When you put a methyl, what happens? So, I can start from here. So, if I put a methyl here, so there will be a methyl now, and this carbon, and I erase that, I put a methyl. So, now I draw the Newman projection. So, if I draw the Newman projection, what will happen? These hydrogens will be replaced by methyls. I hope this is clear. Okay. So, we are talking about the conformation analysis of now 2,3 dibromo, 2,3 dibromo butane. Okay. So, these are the 2 methyls. I replace the hydrogens by methyl, these 2. Okay. So, that methyls are now eclipsed. Now, the question is, when I put these 2 methyls here, that means I am talking about the active form of the dibromo, the optically active form, the optically active form of dibromo, because I can have another form which is the optically inactive form. Okay. We can do that also. So, if I get the optically active form, so so this is, I rotated it by 60 degree, that means the one which I was thinking as hydrogen, I can make them as methyls. Okay. So, this is methyl, this is methyl, and likewise then again when you rotate by another 60 degree this side. So, these 2, so what happens, this methyl, so this hydrogen is a methyl and this hydrogen is a methyl. So, it keeps on it keeps on changing. Okay. So, likewise you can, so the names also you cannot see, the names also you have to be careful. So, better erase all these partially eclipsed. So, we started with this 2,3 dibromomethyl, we converted it into the Newman projection formula, and then we do a conformation analysis. We started rotating the back carbon in an anti-clockwise fashion by 60 degree, and you can draw different conformers. Okay. Now, let us see the different conformations of this 2,3 dibromobutane, which is written in the book. Okay. So, this is a direct representation from the book. So, this is a form, this is 2,3 dibromobutane, the methyl methyls are anti to each other, the bromine bromines are anti to each other. Okay. So, this molecule now is which dibromobutane? This will be the meso dibromobutane, because this molecule is no longer optically active. What it has is what is called a center of symmetry. There is a point in the middle between the carbon carbon bond. When you join this methyl and extend it backwards, you get a methyl. Similarly, that is true for bromine, similarly that is true for the hydrogen. So, it has got a center of symmetry. So, this is the meso dibromo 2,3 dibromobutane, the meso form. Okay. So, the meso form has, this is the anti form, and then you have a, if you start rotating now. So, what is this rotation? Now, you bring the bromine. So, we are drawing different staggered forms. We are not considering the eclipse form, we are drawing different staggered forms. So, this is one staggered form where the groups are really anti to each other. Now, I can have this bromine here, hydrogen here and methyl here. That means, I give an I could do a clockwise rotation now, bromine being here, hydrogen here and methyl there, and that is exactly the bottom carbon. So, this is the same molecule, but given a 120 degree rotation clockwise, and then you do another 120 degree rotation clockwise. Now, this bromine will come here, hydrogen there, and the methyl will go there. Okay. Now, these are what are the gauche forms according to the nomenclature. The bromine are gauche, and the methyl are also in the gauche form. Okay. So, in the gauche form, we have two conformers, and this is the anti conformer. Okay. You start with another molecule where, see, the top configuration, do not change the position of the groups of the top carbon atom. You change, just interchange one of the groups, one of the two groups. That means, you interchange the position of methyl and the hydrogen. That means, you bring the methyl here, hydrogen there. By doing so, you ended up with the optically active isomer of 2,3 dibromobutane. I hope that is clear. So, what I am saying that here there is a I present. So, this is meso dibromobutane, and this is optically active dibromobutane. I got it just by exchanging this methyl and the hydrogen, interchanging the position of the methyl and hydrogen. So, now that center of symmetry is no longer there. In fact, it does not have any symmetry elements, improper elements of symmetry. So, it is optically active. Okay. So, this optically active form now, this is the form where these bromines are anti, but the methyls are gauche form. So, if you now again try to do the same thing, that give a clockwise rotation of 120 degree at the back carbon. So, you get the bromine here, the methyl there, and the hydrogen there. This is another form, and you give another 120 degree. So, now these two bromines are, the bromine is here, the methyl is here, and the methyl is there. So, if you now start calculating actually the energy, you can actually evaluate the energy of these systems, but to know that you have to know certain values. The energy, this molecule suffers from what? Suffers from a bromine methyl interaction, gauche interaction, bromine methyl gauche interaction. Remember what is gauche interaction? When the groups are having a dihedral angle of 60 degree. So, this molecule suffers from Gauss interaction of bromine and methyl to bromine and methyl Gauss interaction. Okay. Gauss interaction of methyl and hydrogen is very little. So, that does not contribute much. Okay. So, Gauss interaction of methyl and bromine to Gauss methyls. So, the question is, what is the energy of a Gauss methyl bromine interaction? We know the energy of methyl methyl Gauss interaction, that is 0.9, and in fact, I think this value, the methyl and bromine Gauss interaction is 0.8 kilojoule per mole, not kilocalorie. Earlier it was kilocalorie. So, that was this was the methyl bromine interaction, Gauss interaction is 0.8. So, this molecule will have energy of 1.6 kilojoule per mole. Okay. This conformation. If it is in this conformation, where the bromine bromine are the Gauss in the Gauss form, so what will be the energy now? First of all, you have to see how many interactions are there. So, there is a methyl methyl Gauss butane interaction that contributes 0.9. There will be a methyl bromine that contributes 0.9, means actually let us see that contributes 0.9 methyl. There will be a methyl, methyl, but remember that 0.9 was in kilocalorie, just there is a change. This is in kilojoule. So, methyl bromine has a methyl bromine Gauss interaction has an energy of 0.8. Maybe I can write it here, that will make it to remember it better. So, the energy values are the Gauss interaction energy values. So, if it is methyl methyl, so I said 0.9 kilocalorie per mole earlier. Now, if it is in kilojoule, it will come around 3.3. So, around 3.3 kilojoule per mole. Okay. Kilojoule per mole, methyl methyl. Methyl bromine is 0.8 kilojoule per mole. Okay. And bromine bromine is 3.0 kilojoule per mole. Okay. So, this is the figure that I have. Now, you can again come back and solve this problem. Okay. The problem is, the question, what is the question? Then the question is, which one is more stable? Is it the is it the mesoform of dibromobutane, or is it the optically active form of dibromobutane? So, how to solve this problem? So, you have to consider all the conformations, all the conformers to be precise. The different conformers you draw, possible staggered forms, they are the conformers. So, this is the mesoform. So, in this form you have 2 methyl bromine Gauss interactions. So, that will be 1.6, 2 into 0.8, and then you have here bromine bromine that contributes 3, then bromine methyl that contributes 0.8, and then methyl methyl that contributes 3.3, and if you add up these, it will come out to be 7.1. And then if you have this conformation, that will be also 7.1, because this Gauss is the mirror image of this Gauss form. So, 7.1 is exactly the same interactions that you have, but you have a conformation which is 1.6 kilojoule per mole. So, that contributes about 80% of the system. Okay. There is a way to calculate also the ratios when you know the delta G, if you know the energy difference. If you consider that there is no entropy contribution here, then you can just write delta G equal to minus RTL and K, and from that you can calculate the percentage of each conformation of each conformer. So, this becomes 80%, and that has got an energy of 1.6. When you talk about the optically active form, you see this is a form where there is a methyl bromine interaction, that we already know that methyl bromine contributes 0.8. There is another methyl bromine that contributes 0.8, and there is a methyl methyl that contributes 3.3 kilojoule. So, the total will be 4.9. And when you have this other conformation where bromine bromine is gauche, methyl methyl is anti, there are methyl bromine interactions, bromine bromine interactions, and methyl bromine interactions. If you add these up, it will be 4.6 kilojoule per mole, and there is another one which is this methyl methyl gauche form. There is a third possibility where you bring this methyl here, the bromine goes there, and you can calculate the energy here. Here the energy will be bromine bromine and then methyl methyl. If you add this up, that will be 6.3, 3 plus 3.3, that will be 6.3. So, whatever you do, you cannot find a conformation which is as low as 1.6. Okay. So, the lowest is 4.6, then 4.9, then 6.3. Here the lowest is 1.6. So, you can say by this conformation analysis, see, so many things are that can be arrived at, so many conclusions, that what are the preferred conformation that you can do, like N-butane, what is the preferred conformation? We have seen the anti-form. Then we can also, by conformation analysis, we can tell between an optically active form and a mesoform, or between two optically active forms which are stereoisomers, which one is more stable. Then you can do this conformation analysis, and if you know the values of the gauche interactions, then you can tell which stereoisomer is more stable. So, you can say that the mesoform of 2,3-dibromobutane is more stable than the optically active form, okay, by this simple conformation analysis. Of course, provided you have these, provided you have the gauche interaction data, okay, and those are calculated, they are found from various experiments. Okay. So, that is how that ends up the conformation analysis of acyclic systems. So, next day what we will do? We will do the conformation analysis of cyclic systems, because they are cyclic systems are not that flexible, because it is a cycle, and the shorter the cycle, it needs 3 atoms to form a complete cycle. The first cycle is a triangle, then it comes a quadrilateral, then a pentagon, okay, then hexagon, like that. So, as the size is, if the size is very small, then there will be more strain in doing the rotation. So, free rotation becomes much more restricted in cyclic systems. However, still you can find different conformations in cyclic systems, where the number of atoms forming the cycle is more than 3. Only the cyclopropane, where there are 3 carbon atoms, that is extremely rigid. You cannot move it up and down, or you cannot do any rotation. But beyond cyclopropane, we will see from the next lecture that there is a conformation analysis possible, that means different conformations are possible in those systems, not in cyclopropane. So, that will be in the next day. Thank you.